Welcome back, everybody. Today we're going to start implementing collision detection and proper physics for our game engine. And usually in 2D games you'll run into walls that you can't get through, or the characters that you're trying to run up against, they won't let you through. There's a collision detection there that says, hey, there's a solid object here, you can't pass through. And usually in 2D games there's also some basic acceleration going on. You don't just immediately start walking and go full speed. There's a gradual, you slowly start to walk and then maybe you build up into a full run. So we're going to add a very basic physics equation into our character movement, and we'll create a new class called the character class. That way all of the movable characters in our game have access to this physics equation. And we'll also make a map class that contains all of the walls in our level. So all of the walls that we want to run up against and not let the player through, we'll contain those in a map class. So I already have Visual Studio up and running here. Let's start by creating the map class. I feel like the wall collisions will be a good place to start. I'm going to right-click Game Engine, Add Class, and I'm going to call this class Map. First things first, let's copy over the using statements from one of our other classes to make sure map has all of the FNA stuff we'll need. And also, let's make this class public because we want everyone to access the map. Right below the map class declaration here, I'm going to make another class called wall. So I'll say public class wall. And this will just be a simple helper class. It won't do very much. It will just hold the rectangle of the wall and a bool to tell us if this wall is active or not. So nothing too crazy here. So let's define the two variables we need. The first one is a public rectangle called wall. The second is a public bool called active. Let's give this a default constructor, empty constructor. And let's also make a second constructor that takes in a rectangle called input rectangle, and we'll just set this rectangle that we're passing in to be our wall. So we'll say wall equals input rectangle. And that's it for that class. Now we can go back up to our map class, and the main thing our map is going to store is a list of walls, right? So our map will have a list of a bunch of rectangles that represent walls that we're not allowed to pass through. Next, we can define how big we want our map width to be. I'm going to say 15, and we'll have a map height, and I'll set that to 9. And then finally, we need to define a tile size, and this is how big each grid on our map will be. So when I say the map width is 15, that's 15 tiles wide. And when I say the map height is 9, that's 9 tiles tall. So how big are each tile? And I'm going to say each tile is 128 by 128 pixels. So 128 will be applied to the width and the height. In a lot of 2D games, you'll see 128, 128 as a common tile size for the maps. And finally, up here underneath the list of walls, let's make a texture 2D called wall image. And whenever we're drawing our walls in our game, we want something to represent it. So in our case, we'll just load in a pixel and we'll color that black, and all of the walls in our level will have a black box to show us where the walls are. Otherwise, if we don't have something representing that, we'll just have invisible walls, and when we're designing our levels, that's usually not a desired result. Right? We usually want something to represent the walls, and then later on, when we add in more images, we can add pretty decorations on top of the walls to make them look more presentable. But for now, let's go down here and say public void load, and we'll take in a content manager called content. And in here, I'll say wall image equals texture loader dot load pixel, that's the name of the image we'll load in just a second, and then we'll pass in the content manager so that image can be loaded. And for this pixel image, if you go to the Michael Hicks toolbox, inside of the art folder, there's a image right here called pixel. Let's go ahead and drag that and drop it into our content folder in Visual Studio. And then remember, for every image we put in here, we have to change some settings. So I'm going to click sprite and then, or I'm sorry, I'm going to click pixel, that's the new one. And I'm going to say copy to output directory, copy if newer, and that's going to move this image next to our executable file when we build our game. Now we can go back to our code, and I'd like to write two other functions in our map class. The first one I'd like to call check collision, and it will return a rectangle, and it will take in a rectangle called input. And what we're going to do here is we're going to pass in a rectangle called input, and this input rectangle will usually be the collision box that surrounds our player. So this rectangle represents basically how wide and how tall the player is, and we will use this collision box to test against all of the walls in our level, and if the player's collision box collides with any of the walls, that means there's been a collision and we need to stop moving the player. So we will iterate with a for loop through every single wall in our map. So we'll say as long as I is less than walls.count, I++, and then here we'll say if walls at sub I, so if the current wall we're looking at is not equal to null, and the current wall we're looking at, if its wall, so maybe this is a little confusing terminology, but remember the walls is our list, and we're looking at the wall, which is the actual rectangle here. If the actual rectangle of our wall intersects with the input rectangle that was passed into this function, that means there's been a collision, and we will return the rectangle of the wall that was collided with, right? So, hold on, let's also say return rectangle.empty. So if there were no collisions, we'll return an empty rectangle. But if there was a collision, if two rectangles are intersecting with each other, we will return the wall in our level that was intersected. And this is useful if we want to maybe later on detect more specific information like what position this wall was at, things like that. This way we'll have more detailed information of the collision. So basically this will return a rectangle that has data in it as long as the input rectangle that was passed in is colliding with or intersects with any of the walls in our level, okay? So this is a very basic collision detection function. It returns a rectangle with information if it's true, there was a collision. It returns an empty rectangle if there was no collision. Down here, let's write our final function in map. I'm going to call this draw walls, and we'll pass in a sprite batch to draw with. Like I mentioned earlier, we need a way to visually draw all of the walls in our level onto the screen, and we'll just do that by drawing everything black. So wherever there's a wall, you'll see a big black box. So to draw all of the walls, we'll iterate through all of the walls. Just like before, we'll say I equals 0 for as long as I is less than walls.count, I++. If the current wall we're looking at is not equal to null, and the current wall we're looking at is active, we'll use sprite batch to draw. So we'll say sprite batch dot draw. Wall image will be our texture. For the position we want to draw at, we will say new vector 2, and we will pass in the x and y position of the current wall we're looking at. So we'll say walls I dot wall dot x and walls I dot wall dot y parentheses, That's pretty straightforward. That's just the X and Y position this wall is currently at. Next, for the source rectangle, we can pass in walls I dot wall. And the source rectangle is a rectangle that represents how big of a portion we want to draw. So sometimes when you're using a sprite sheet, which we'll do in a later video, on sprite sheets you have many different frames of one animation. So say you have a guy running to the right, there'll be like maybe 15 different images on one sprite sheet of him moving, like a flip book, right? We'll have to specify which frame we currently want to draw on that sheet, and the way to do that is by passing in a source rectangle, which will only draw a certain chunk of the image. In this case here, we want to draw that 1 by 1 pixel. We want to draw that scaled up, basically, to cover our entire wall, because our walls might be 128 by 128. If we just draw a 1 by 1 pixel image, that's not going to cover the whole wall. So when we pass in this rectangle here, that will make the image scale up and cover our entire rectangle. Okay? I feel like the source rectangle will make more sense once we do sprite animations in a later video, so if that doesn't make too much sense, I think it will once we do the sprite sheets, so don't worry too much about that. For the draw color, I'm going to pass in color.black, so all of our walls draw black. For the rotation, I'll pass in 0f. For the origin, I'll pass in vector2.0, so it draws in the top left corner. For the scale, I'll pass in 1f. And then sprite effects.none. And for the layer depth, let's just draw all walls at 0.7. So our game objects default at drawing at 0.5, and that will make our player draw in front of any wall. Remember, I talked about the back to front ordering in the last video, and this is where that comes into play. So now we have our map class 100% completed. We have a list of all the walls in our game, and we're checking for collisions, and we're drawing the walls. How about we plug in this map class into our game1 class and actually make it do something? So let's go back to game1.cs, and at the very top here underneath our objects, I'm going to make a new map called map. That's easy enough. And then below in the draw function, right under draw objects, I'll say map.drawWalls. That way our walls can be drawn right after our objects have their function called. Down here in our load level function, we can add some walls after we add our objects. I'm going to say map.walls.add new wall, and here we can pass in a default wall for this wall to initialize at. I'm going to say new rectangle 256, 256, 256, 256, and that's going to make a new wall that is drawing at the X and Y position of 256, 256, and it will make our wall 256 pixels wide and 256 pixels tall. Semicolon at the end. Let's go ahead and copy and paste this line, and we'll make one more wall. This wall I'd like to represent the ground that we'll be walking on. So this will just be a long rectangle wall at the very bottom of the screen. Let's start this at 0, so it starts on the left side of the screen. Let's move it down on the y-axis to be about 650. Hopefully that will be at the bottom part of the screen where we will be walking. And let's make this 1280 wide, because our game window is 1280 pixels wide. And then I'll just make it 128 tall. So we could press F5, but we're not quite ready to see our walls in action yet. We need to go up to our load function, and right before our load level function, we will say map.load, and then pass in our content manager so we can load in that wall image to draw the walls. Now we can press F5, and we should see something. Hey everybody, this is an edit I put in later in the video. When you press F5, you actually will not see your walls. And I actually lost the video footage of me fixing this. So I'm going to recommend that you try and debug where you think the problem is, because I think this is a good debug exercise. I'll give you a hint. A good place to drop a breakpoint would be in your draw function in the map class. If you cannot figure out what's wrong and why your walls aren't drawing, I'm going to put the line of code on the next slide here when I stop talking, and you can fix it like that, but I'd encourage you to try and find the problem yourself. So here's the code, and after that the video will resume. Sorry about that. And there we have it, right there. Over here to the left we have our 256 by 256 wall we defined first, I believe. And here's the second wall we defined. It was the 1280 wide wall that extends from the left of the screen to the right of the screen. Notice that we're still able to walk through these walls, nothing is stopping us, and that is because the player does not have any type of data to store and detect collisions. We don't have a bounding box like the walls do. We need to create one. But before we just dive in and give the player a bounding box rectangle to check for collisions, won't all of our game objects need a way to detect for collisions? And the answer to that is yes. Even if we have a game object like a power-up, the power-up won't stop us from moving, so it won't behave quite like a wall, but we would still need to detect when the player collides or walks on top of the power-up, so we know that it's time to apply the power-up to the player. So, since all game objects need collision information, let's go to GameObject.cs over here, and we will give GameObject some variables to detect collisions with. So I'm going to make some new spaces here, and the first thing I'm going to make is a public bool called collidable. I'm going to default that to true, and sometimes, like I mentioned earlier with the power-up, sometimes we want our game object to stop the player from moving, similar to how a wall behaves, but other times we want the player to be able to walk through our bounding box. So if we were a power-up, the collidable bool would be set to false, but we'll just leave it at true for now. Next, let's make two protected ints. The first one we'll call bounding box width, and the second one we'll call bounding box height. And this is where we will store how wide and how tall our bounding box is. Each game object can customize these variables to be different numbers. Now we will make a vector 2 called bounding box offset. And sometimes when we're making our bounding boxes, we want to move the bounding box over to the left or to the right. We want to offset it a little bit to be more tightly fit around the image that we're drawing. So this variable will be used for that. Next we will make a texture 2D called bounding box image, and this will work just like the image we used in map. On the next line we'll make a const bool called draw bounding boxes. We'll set that to true. Whenever a variable is marked with the const keyword, that means it's constant. And basically that means whatever we set this variable to, it can never be changed again. So when Visual Studio compiles our game, it will basically go through and replace everywhere it says draw bounding boxes, it will take that out and just put true there instead in our code. We'll use this whenever we are testing our game to make sure the bounding boxes are positioned correctly and working correctly. We will want this to be set to true so we can actually see them on the screen. But whenever we want to view the game normally without the bounding boxes drawing everywhere, we would set this to false. Finally, I'd like to make a property called bounding box. It will be a rectangle. And properties are a new concept, I believe, for us. Think of them like a variable. They work just like a variable. But before we return the data to use, we can do some calculations on the data beforehand. So in our code, whenever we say, hey, let's use the bounding box, this property will run some extra calculations on the bounding box before returning it to us to use. So properties work kind of like functions. We will add some curly brackets here. And inside we will say get, and then add in another curly bracket. And whenever we call bounding box, this get line here will be called. And inside get, we can return a new rectangle. Here we will just build our bounding box like normally. So the x position of our bounding box will be an int, and we'll make a second set of parentheses here, and inside this set of parentheses we will say position.x plus bounding box offset dot x, comma, outside that parentheses, and we will now say int, parentheses. Inside of the second parentheses, we'll say position dot y plus bounding box offset dot y, comma. Here it's asking for the width and height, so we'll say bounding box width, bounding box height, with a semicolon at the end. So notice that the x and y values inside of our vector2 position, they are floats, and rectangle requires the x and y positions to be ints. So that's why we are casting or converting this calculation into an int. Whatever the result is of position.x plus bounding box offset.x, we will then convert that to int. Remember that bounding box offset is how much we want to move the bounding box to the right or left, or up or down. Finally, we'll pass in the bounding box width and the height to set the size of our bounding box. And the reason we want to use a property here is because it's possible that our position can be changed during each frame. So if we call our bounding box and the position has been changed, it's possible our bounding box can be out of date. So whenever we set it up like this, each time we call bounding box, we are calculating it with the current value of our position, so we know the bounding box is for sure up to date. Next, let's go down here to our load function. First things first, let's load in the bounding box image, just like we did in the map. Let's say texture loader dot load pixel, comma, content. Underneath the calculate center, we will calculate the default bounding box width and height. So if our image is not equal to null, we'll just set our bounding box width to the image's width. Same thing for the bounding box height. We'll say bounding box height equals image.height. We can customize these variables later on in the deriving classes. So if we want our player.cs class to have different width or different height for the bounding box, we could overwrite these variables later. But for now, let's default it to the image's width and height. So our bounding box for the player should automatically be 128 by 128. Now we can go down here to the draw. This is the final part of the game object implementation. We will draw the bounding box for each game object. So if the bounding box image is not equal to null, and we want to draw the bounding boxes, and finally if the current game object we're drawing is active, if all these things are true, we will draw the bounding box. I'm going to copy and paste that sprite batch.draw call and use it here. Let's just replace some of these variables. So instead of drawing the game object image, we will draw the bounding box image. For the position, we'll pass in the bounding box's position. So new vector2, bounding box.x, bounding box.y. For the source rectangle, we can pass in the rectangle for our bounding box. For the draw color, I'd like to do something a little different here. This rectangle will be drawing on top of our player sprite. So we don't want the rectangle to completely cover the sprite so we can't see it. I'd like this rectangle to be a little bit see-through. If you remember in the last video, our draw color was set to 0, 0, 0, 0, and we couldn't see it at all. That's because when it's all zeros, it's completely transparent. But when the color is set to 255, 255, 255, 255, that means it's completely opaque and it's not see-through at all. So for this bounding box image, I'd like it to be somewhere in between. I'd like it to be just slightly see-through, but still have enough value where we can see the rectangle. Okay, so let's say new color 120, 120, 120, 120. That's somewhere in the middle of 255 and 0. Not perfectly, but should be good enough. For rotation, let's say 0f. For scale, let's hardcode that at 1f. And then finally for layer depth, let's hardcode that to 0.1f. So the box should draw pretty close to the screen. It will definitely draw in front of the player, because the player is 0.5. Let's press F5 and hopefully we'll see a bounding box around the player. And we do. Check it out. So there's our 128 by 128 bounding box, and it's constantly synced up to where the player is at. Notice it's always up to date. But if we try to move through these walls, we're not stopped. We're still able to walk through them. That's because we have our data defined, but we're not actually calling that check collisions function inside of map. So let's exit out here,